So today's topic, I'll be talking about using martingales to analyze random walks. So the first case is the simple symmetric random walk, where we have IID random variables that take on plus or minus 1, each with probability 1/2. So Sn is the sum of the first n steps, or just the state of the random walk at time n. So Sn is a martingale with respect to the natural filtration. So if we define t as a stopping time, or the smallest n such that the random walk crosses a boundary, either the upper boundary or the lower boundary. Our problem is to find the probability of hitting one border first. So we'll define PA as the probability of striking the lower boundary first. Now, the fact of martingales is that at the stopping time, the expected value is equal to the expected value at the initial state, which in our case is 0. So now we can compute the expected value of the random walk by substituting in the values of the random walk at the stopping time. So it either takes on value of negative a with probability of hitting negative a first, or b with probability of hitting b first. And this expected value equals 0. So we can then solve for the probability of hitting a first, which is just the ratio of the value of the lower boundary, or the upper boundary, excuse me, and the lower boundary. Our second case, we look at the random walk with drift. So now suppose that the probability of one step going up is p, and the probability of taking a step down is 1 minus p. Again, we define the state of the random walk as the sum of each of the steps up to time n. Now, this is not necessarily a martingale, but we can account for the drift to make sure that the property holds. So we'll define the new martingale as the state at time n minus the expected value of the state at time n. Computing this, we see that it's the expected value of the sum, and by linearity of expectation, we can move the expectation through the sum, and the expected value of this is just 2p minus 1, again referring back to the definition of the random variables. Summing this, we get n times 2p minus 1. Defined this way, this is a martingale with respect to the same filtration as before. Now, we'll let t be the smallest time when the random walk crosses some boundary. This is still a stopping time. We want to find the expected value of the stopping time. At time t, the value of the martingale is the random walk at time t minus t steps times the expected drift. This is just x, the value of the boundary, minus t times the expected drift. Using this, we know that the expected value of the martingale at the stopping time is again equal to 0, or the martingale at the initial state. So we have 0 is equal to the value of the random walk minus the expected value of the stopping time times 2p minus 1. Solving for the expected value of t, we find that it's simply x over 2p minus 1. Now, this will hold so long as p is greater than 1/2, or we don't want this drifting off to negative infinity. Now, in the next case, we can use product martingales to analyze random walks and their hitting times. So we'll have the same conditions as before, IID random variables, and it's possible there is some drift to this. We'll let t be the smallest time that we hit one of the two boundaries, and this is a stopping time. A product martingale we will define as such, or the exponential of some value theta, the random walk at time n minus n times some function psi of theta. The expectation of the product martingale is 1. Now, for our condition, we assume that theta is non-zero, and we also assume that psi of theta is equal to 0. This will ensure that our increments also have expected value of 1. Again, our stopping times are defined the same way. The expectation of the stopping time then is simply applying the value of s of t, so that could be either b or minus a, with probability q or 1 minus q. Now, the expectation of an increment is also 1. So the value of this could take on either 1 or -1 with probability p and 1 minus p. Now if we take the log of both sides, we can then solve for this value of theta. Find that theta is log of 1 minus p over p. Now, substituting this back in to our original expectation, we can then solve for q. So applying these logs, the log cancels the exponential, and we get this expression, which when solving gives us this expression for q, or the probability of hitting b before a.